Today we're doing lesson 2.3.1, and we'll be working off of this guided practice sheet. Okay, the one that's labeled 231. How can I make a useful graph? Okay, so we're going to do a little shift for 2.3 lessons and talk about displays, data displays. So we're talking about Peyton's bats. Peyton loves bats. She wants to know if she can predict the wingspan of a bat by knowing the length of its body. Peyton has started a graph, and her work is shown at the right. So here's a table that she used to record the length of the big brown bat and its wingspan, little brown bat, Brazilian evening bat, and the Indiana bat. Now, if we're looking at the graph, this is the graph that represents the wingspan and the length of the bats. So we see a point here, and from that location we can see that on this x-axis it's at about 3, and that point on the y-axis is about 10. And then all these other points coincide with the x and the y. We can find the ordered pairs. So the first question is asking which axis represents the length of the bat. Okay, now these are the lengths of the bat, and which axis, the x or the y, represents those. So we can see, looking at the x-axis, we see that the largest value for the x-axis is 5. But then the y-axis, this is the largest value here because it's the highest, and that's about 14. So looking at this table, you can see that the wingspan, largest, is 14, and the length is 5. So that means that the length of the bat is represented by the x-axis. The x-axis is the length. So the axis that represents the wingspan would then be these, because the highest is 14 on the y-axis, so that would be wingspan. Y-axis is wingspan. Okay, so the way we would be able to tell is we looked at the largest values. Okay, so we picked one of the largest values, that's 14, and that's 5. When you are sure, label each axis. So let's go ahead and label that first one, length of the bat. Okay, so very important whenever you have a graph that you have your x and your y labeled as what they represent. All right, what is the scale on the horizontal axis? So horizontal would be the x-axis right here, and let's go ahead and label that as well. Let's label this as x, and then we'll call this the y. Okay, so what's the scale? What are we counting by on these? So that means, in other words, what is every one of these intervals? So if we're starting here, this is the corner, this is the origin, we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those seem to be the numbers that we are talking about. So the scale, we are counting by ones. What's the scale on the vertical axis? Is it the same? Are we counting by ones on the vertical axis? We are counting by ones as well. Is the scale appropriate for graphing this data? So they're asking, is this an appropriate graph for these numbers here? And what it kind of looks like is the graph is pretty big in size of the amount of space that we can use, but how much of this space did we actually use? Okay, so out of this whole entire graph, all we're using is this tiny little bit right here out of this whole entire graph. So does that seem appropriate, or is it kind of wasteful? It seems kind of wasteful in this sense. So is the scale appropriate? It looks a little bit too squished. Not exactly a math term, but we're going to use that to represent that our data is kind of all mushed up together in one general area. Okay. Now, Peyton wants her data to be spread out, obviously, so she can see a relationship clearly. Because if we look at this data, everything's just kind of muddled into a tiny area. We can't tell if there's some kind of a positive or a negative relationship. Okay, and you know what a positive and negative relationship looks like. If we have a graph right here and we have a positive relationship, we can kind of see the trend going upwards as we go from left to right. And a negative would be going from right to left, going down. Okay, so these are the trends that we want to see. So we can't really see it when our data is all mushed up like that. So does the graph allow her to see spread out data? Okay, so this is a no. We cannot see a relationship. Okay, because it's too squished. Are there any changes you can make to a graph that would make it clearer? Be prepared to explain your ideas to the class. So what can we do so that this data is nice and spread out? Okay, so one example that we might say, someone might have said it already, is we can count by different intervals, use different intervals. Okay, so that means instead of counting by ones, we can count by something else that might make that a little bit different. Okay, so Peyton has an idea. She says, I will make the numbers on the horizontal axis bigger. Okay, so instead of counting by ones, what is she counting by now? So we can see this is 10 right here, so she must be counting by 2, 4, 6, 8, 10. She's now counting by twos. Okay, so she's using a bigger number, and that's going to be her interval. So Peyton's new axis is shown at the right. How has Peyton changed the scale, and will all of her data fit on this new graph? So let's see how this new scale has changed it. So let's graph. So our first point, the big brown bat, we're going to go to 514. Okay, so here's the length. Let's label those again to keep them together. And the wingspan is here. Okay, so by counting by a bigger number, let's see what it did. So 514, the length is 5, and that'd be 2, 4, so that'd be here. And then the wingspan is 14. So here's 10. Actually, on the y-axis, it looks like she's still counting by ones. So 514, 2.5, 2, 4, and then halfway is 5. And then here's 5, 10, 11, 12, 13, 14. So here is 514. Okay, our next point is 3.5, 10. Okay, so there's 2, 4, so 3.5, 10 is about right here. Okay, next point is 4.25, 12. 2, 4.25, and then 12 is right here. Next point is 411. So x is 2, 4, and y is 11. That's right here. And then 310, 2, 4, so there's 3, and 10 is right there. Okay. So it's pretty close to 3.5, 10, but you see how 310 and 3.5, 10 just kind of munch up together. So what has happened there? Is this graph easier to read? There are 1, 2, 3, 4, 5 points there. It's kind of hard to even tell that there's 5 points. So is it more spread out? Look at this one. Look at this one. More spread out. All right, so what you should have noticed is that they are not more spread out. Okay, so how has Peyton changed the scale? So what happened is the x-axis has an interval of 2, okay, instead of 1, the interval of 2. And will all the data fit in the graph? It looks like it all did fit. Okay, so all the data fits on the graph. Will Peyton's new graph be more useful? And discuss this with your team and then test the ideas by plotting the data points on the new set of axes. So we already did that. And is this data useful? Is it more useful than this data? Okay, so what you should have figured is this is not useful because the points are hard to see. There's 5 points there, and it only looks like there's 4. So it's hard to see. It is too squished. Okay, or we can say it's more squished, more than before. Okay, so when we counted by intervals of 2, which Peyton thought, oh, this is a good idea. If I use bigger numbers, it's going to be more spread out. But when we counted by 1, it seemed to be more spread out. Okay, so what's going on here? We counted by 1, it's more spread out than if we counted by 2s. So what do you think would be a good idea? So Peyton's come to us for help, and let's decide on a scale for each axis that we could use. Okay, so we need to make it so it's easy to see. How can we spread out this data, in other words? Okay, so what do you think? Okay, so what you might have come up with is, first, let's go ahead and label these again. Very important to always label your axes. Okay. One idea that we might be able to use is let's count by fourths. Okay, so here's 0, 1/4, 2/4, 3/4, and this would be 1. 1/4, 2/4, 3/4, 2, 3, 4, 5. Okay, so what this does, this spreads out from 0 to 5. 5 is the longest length, and if we look at this data, 5 is the longest length. Okay, so and that takes us all the way to the end of our graph. And as far as our y-axis, will the same y-axis be useful? And I think it might be kind of spread out a little bit more. So let's go ahead and count by ones again. So we have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we want to go just a little bit more or a little bit higher than what numbers we're given. Okay, so we can do that. Now let's go ahead and plot those points. Okay, so the big brown bat, the length is 5, the wingspan is 14. So let's plot that on our brand new graph. 5 is right here. There's 514. The little brown bat, 3.5, 10. So here's 3.5, and we're going to go up to 10. Where does 3.5 and 10 meet? It meets right here. 3.5, 10. The Brazilian, 4.25 and 12. So here's 4.25. Good thing we use quarters. And 12 is right here. Oh, I see a little bit of a trend happening here. 411 is the evening bat. 411. That's right here. And then we have the Indiana bat, which is a length of 3 and a height of 10. Okay. So if we look at our data, we can definitely tell that it's more spread out. We might have even been able to use a smaller number than 1, maybe count by halves or count by thirds or something to spread it out even more. The smaller the interval, the more spread out your data is. All right, so one thing we can do is kind of make a line that we call the line of best fit. And the line of best fit is, if I were to take this data on this is called a scatter plot, where we're collecting data and it's kind of aligned a little bit, we can call a line of best fit goes from the origin and kind of through the middle of our data. So if I were to draw a line through the middle of our data, it would probably go somewhere like this. This looks like it kind of goes through the middle of that data. So if we were to predict something, okay, so here's how we can use those points to predict. If I have a bat that's a length of 3, it's going to be close to that line. Okay, it's at 10, but it's kind of close to the line. If a bat is 3.5, it's on the line for 10. If it's 4, it's on the line for 12. See, we can use that line to predict what the wingspan is going to be because they all align with our line of best fit. So here's how we can use it to predict. Let's say that we want to find what is the wingspan of a bat that is 2.5 feet of length. Okay, so if the length is 2.5 inches, what is going to be the wingspan? Okay, so what would it be? According to this line represents the relationship between length and wingspan. So we look at the length of 2.5, it's about right here, and it looks like the wingspan is going to be about 7. Okay, and let's try one more. What if we have a bat that is 1 inch in length? What would be the wingspan? Okay, and what you should have is, here's 1, it would be about 3, approximately 3 inches. And that's how we can use a graph to predict.